here we go. We're recording. All right. So today we're going to start with an area problem. We want to find an area of a region. This region involves some equations in polar coordinates. So we're going to end up setting up an integral with polar coordinates. But you notice these two are in Cartesian coordinates, so we might have to. So we're going to have to convert them to polar coordinates before we set it all up. First thing I want to do is take the description of this region and get a nice there we go, a nice picture of this for us to draw all over. So got my Desmos over here. So let's type these equations in. We're going to have the line 2y equals x plus 2. Okay, we're going to be bounded above by that line, all right? So our region is going to be below that line in the first quadrant. We're only going to be in quadrant 1 over here. It's bounded below by the line y equals 0. So if I graph y equals 0, our region is above that one. So bounded above by the red line up here and below by this blue line. Okay, so we're between those two lines. Then we're bounded on the left by the circle r equals sine theta. So if I graph r equals sine theta, here we go. That is this green circle over here. So that is a left boundary. So that means that our region is like outside of that circle. And then we're bounded on the right by the circle r equals just the square root of 8. That is a constant radius circle centered at the origin. So the region we're looking for is inside here. Okay, I'm going to grab this, snap a picture, and pull it over for us to work on. That's a little bit bigger than it needs to be. Just like that. Oh, no. There we go. All right, so here we go. Here is our picture. We want the region, let's see, in here, basically, that region right there. Okie doke. So let's label our graph. We have on top in red, this is the line 2y equals x plus 2. On the bottom, we have the y equals 0 line. On the left, in green, over here, we have the r equals sine theta. And on the right, in purple, we've got the r equals square root of 8. Okay, so these two are already in polar, so they don't need to be edited or changed at all. Those are already written in polar coordinates. But what we want to do is write our other two in polar coordinates as well. Let's start with the bottom one. Y equals 0. Y equals 0 is a line, straight line passing through the origin. If you have a straight line passing through the origin, it's pretty easy to describe in polar coordinates. What do you guys think it's going to be? Polar coordinates, y equals 0. What is this line described in polar coordinates? All right, so we can replace y with r sine theta equals 0. Okay, we could do that. If r times sine theta equals 0, what do you think? If I divide both sides by, say, sine theta, I could get r equals 0. But what's r equals 0? That's just a point. That's just the origin right here. So that's not very interesting. If I divide both sides by r, I get sine theta equals 0. What's the solution to sine theta equals 0? Theta equals what? Just theta equals 0. There we go. I think that is a good description of this line, because the points on this line here are all of the points in the plane where the theta coordinate in polar coordinates is equal to 0, right? So that looks pretty good. Now over here, we have a point where the blue and the green meet. At that point, we have theta equals 0. And at this point over here, where the purple and the blue meet, at that point, we likewise have, man, between purple and blue is hard to grasp. There we go. At that point there, we have theta equals 0 as well. Okay, so theta equals 0 is going to be one of the boundaries of this integral, one of the limits of integration when we finish setting it up. Now let's turn our attention over here to this situation. This 2y equals x plus 2. Let's convert that to polar. 2y. Now y is r sine theta equals x plus 2. Now x is r cosine theta. There's the equation converted to polar coordinates, but we want to solve that for r and get r as a function of theta. So we will subtract the r cosine theta from both sides, moving it from the right-hand side over to the left-hand side. Then we will factor out the r. And solve for r by dividing. So r equals 2 over 2 sine theta minus cosine theta. And that is our equation for that line in polar coordinates. Okay. Now, one of the things we're going to need to know, besides these lines in polar coordinates, we also should know the angles, right? If we trace a ray out from the origin, that ray, like going out like this, okay, it's sort of, we're going to think about where does it enter the region and where does it exit the region. That ray there enters the region on the green curve, and it exits the region through the purple curve. Let's draw another ray a little further up. So for a higher angle like that, that also enters on the green curve and exits on the purple curve, right? There we go. But if I draw my ray a little higher, do it like that. Now I'm entering the region on the green and exiting on the red. And that remains true until we sort of throughout the rest of the region. So I'm imagining rays passing through the region, starting from the bottom, the smallest theta value, and ranging up to the highest theta value, right? So it is going to be important for us to pay attention to certain angles. This angle is important, which is the starting angle. This angle is important, which is the angle at which the like outer boundary of the region changes from the purple to the red. And then this angle is important, which is the angle where we finally exit the region. Okay, so let's identify those 3 points: this point, and this point. What are the angles associated with those points? This one we already have, right? We got it over here. I wrote it in blue, but I'll write it in black. This is theta equals 0. This one's pretty easy. The red and the green curves intersect right here on the y-axis. So that angle is 90 degrees, or in radians, pi over 2. What is this angle? What is it up here? Theta equals what? Fairly easy to figure out just by looking at it. The coordinates of that point are 2, 2, right? 2, 2. In general, we can use the equation tangent of theta equals y over x. So theta is going to be the arctangent of y over x. In this case, it's the arctangent of 2 over 2. Okay, and that's the arctangent of 1. And the arctangent of 1 is pi over 4. Okay, so this is a fairly easy angle. It's like the 45-degree angle, right? That's 45 degrees there. Right? It's pi over 4. But if it was not an obvious angle, like if the coordinates of the point of intersection were like, for example, like 3, 8 or whatever, then you would say, well, the angle is going to be the arctangent of 8 over 3. And then you could get that value, you know, arctangent of 8/3. And Desmos is by default set to radians over here, but you might, you need to, if it's in degrees, it gives you 69.4, but if it's in radians, it gives you 1.21. So you want it to be in radians and make sure and then you probably just estimate that, you just round that and use that number. Okay. So there we go. So just a little aside about how to figure out angles from coordinates of points. Okay. So now that we've gotten this far, it's time for us to start setting up an integral, or perhaps actually, I guess, 2 integrals, one for each side. Does that make sense? We want the 1/2 and the other half, right? So we want to kind of split this into 2. We could say, let's shade one of them a different color. Let's say this side we've got, the light blue, and that side we've got the light orange, right? Yeah, there we go. That's fine. There we go. So for the light blue region, which we'll call, go ahead and call that like region A. Oops, region A, and this will be region B. Okay, so A, we're going to do an integral. We're gonna look for the starting and ending theta values. Those are 0 and pi over 4, right? It's those starting and ending theta values. And then what we want to do is figure out, we want to use the area equals integral of 1/2 r squared d theta. That is our formula we came up with yesterday. Okay. It comes from doing that Riemann sum with sectors instead of rectangles. Remember that? We want to do that. But because there's an outer curve and an inner curve, we have to like subtract. So this is kind of like when we were doing that stuff in chapter 2 with areas between curves, or like volumes of revolution with like the washer method and stuff. It's very similar to that. We're going to do 1/2 times the outer radius squared minus 1/2 times the inner radius squared, and then integrate that with respect to theta. Okay, so outer radius, inner radius. That's basically going to take the total area minus this little tiny slice down here that we're supposed to cut out. You can see right there, there's that slice which is not shaded. We have to remove that. Okay. That's what this subtraction is going to be for, right? So let's see, 0 to pi over 4. Outer radius is the square root of 8. So this is going to be 1/2 times the square root of 8 squared. That's just a constant radius. It's nice and simple. And then the second one over here, the function that describes this green curve down here is our r equals sine theta. So we're going to do sine squared theta. Right, squaring that r. Pause to blow my nose. That's the first region. That's the A region. Okay. light blue. Next, we'll do the B region. Pause. Before we do the B region, any questions about how we set up the integral for the A region? Maybe I should rearrange this a little bit. I'll just make this one general, alpha, beta, and have this one be A. And then I'll kind of scoot this up as a general formula for area between curves. And this specifically is for the A region right there. And then we'll do the B region. We'll apply the same formula. Okay, so now for the B region, our angles are going to range from pi over 4 to pi over 2. So integral from pi over 4 on the bottom up to pi over 2 on the top. And then we're going to do our 1/2 times the outer radius squared. So our outer radius is given by the red function. So we'll do 2 over 2 sine theta minus cosine theta, and that whole thing is squared. And then minus 1/2 times the inner radius squared, which would be this green thing again. So again, it's going to be r sine theta. So, sorry, just sine theta. So 1/2 sine squared theta, d theta. Now, that is our orange region there. And we're going to add these two together, A plus B, to obtain our total area. Okay. So, how would we actually do this? Well, this is just 1/2 times square root of 8 squared. That's 8. 1/2 times 8 is just 4. So that is a nice, simple integral to solve. I think that integrating sine squared is pretty simple as well. We have done that plenty of times before, right? So on this, so this one I'll just say easy. This one I'll say trig identity, right? You know how you use the power reducing identity to solve something like that. You do that. And then for the first term here, we'll have integral pi over 4 to 4 to pi over 2. Gosh, okay, 2 squared is 4. Divided by 2 is 2. So we just have 2. And then down here, we've got this 2 sine theta minus cosine theta, and that whole thing is squared. Question marks. Not sure how we're going to do that one. But then the last one here is another trig identity one, where we're going to do minus 1/2 integral of... Hang on, guys. We added, oh no, we subtracted it. It was minus 1/2. Oh, this is minus 1/2 as well. Okay, never mind. Are these going to combine together? You could probably take these and combine them instead of having 2. I'll just kind of make a point about that here. I'll just kind of say, hey, this guy and this guy that we're subtracting them both, we could combine them together. And just do the integral from 0 up to pi over 2, right? Because we go 0 to pi over 4, and then this is pi over 4 up to pi over 2. They're both times 1/2, so that stays the same. We're subtracting in both cases, that's the same. This integrand is exactly the same. It's all exactly the same except for those limits of integration. So those two intervals can string together into that. Okay. But this is the one that remains. How the heck do we do this guy? Right? What do we do with 2 over 2 sine theta minus cosine theta? Would the negative one, Isa asks, yes. Yes, would the negative 1/2 still be out front? It sure would. So we'd still have a negative 1/2 here, and this would still be sine squared theta here. It would look like that. it would look like that. Yeah. But yeah, this one in the middle, this is the tough one. I think this is another example of a non-elementary integral. I don't think this is going to succumb to any like trig identities or anything like that. This is probably an integral you're going to want to estimate the value of by some method. Estimate by a Riemann sum, or take that function and try to estimate it by a Taylor polynomial. Something like that. Those are the two methods I've taught you this semester, so that's kind of all we have right now. Yeah. So there we go, folks. So that is that's a better example than the one I showed you yesterday, right? Do you want to talk about how to do the Riemann sum for the Taylor polynomial? For that integral? Got a couple of sures. Yeah, okay, let's do it. And then we are going to get back to another thing about, we got to save time for the other thing. We're going to get back to tangent lines, but let's do a Riemann sum. Okay, I'm going to, let's just have that integral alone, just this. Okay, copy that. We'll export this page, and then we'll get a fresh one. Oops. Oops. 28th. All right, there we go. Okay. So for this, we have this function going on. This, I'm just gonna call this x. Oh, look, I wrote an x over here. That was a mistake. I think I should have written a theta there, but it's okay. We're just gonna replace theta with x for now, just to kind of keep things simple. So now we have this function we're working with, right? Oh, nope, that was a mistake too. I'm sorry. Oh shoot, now I feel bad that I messed up a couple of things on the previous page. Apologies. Yes. Yeah, you guys both, yes, you guys got two comments about that. Thank you for catching that. It is pi over 4 to pi over 2, because that was the this interval we were working with. Yeah, sorry about that. Okay, we fixed that up. Good. So now, to set up a Riemann sum, we want to basically imagine taking this function, whatever it looks like. Might as well get a picture of it to work with in our heads. Two over 2 sine x minus cosine x. It looks like that. We really only care about it on the interval from pi over 4 to pi over 2. So that's all. That's what we want. Is just like this little nugget of a curve. It's a little tiny snippet. Speaking of snippet, I'm going to snip it. Snipped it. All right. Oh, is it squared? Oh, you're right. It's squared. I forgot to square it. Oh, you guys are catching all my mistakes today. Sweet. Thank you. This part is indeed squared. It looks like that instead. Slightly more elongated snippet of a curve. Snippet. All right. So we're going to take our interval here, which goes from pi over 4 2 pi over 2. And to set up a Riemann sum, we want to imagine, doing this, breaking up into pieces here, right? Our delta x, width of those pieces is going to be pi over 2 minus pi over 4 over n. So this ends up being pi over 4, which is the distance between these is pi over 4 units long, right? Divided by n, so pi over 4n. So that's our delta x. And then we can do xi, the right endpoint formula for the sample points. Just the simplest of the various sample point formulas you can do. It won't be as accurate as a midpoint formula. Would you like to do a midpoint formula? Maybe we should do a midpoint formula. Maybe we'll do a midpoint formula. Actually, yeah, let's do midpoint formulas. Midpoint equation. So xi bar, the average of the xi's on the ith interval. So that is going to be the left endpoint plus I delta x and then minus a half delta x. Right, so it's kind of like left endpoint, add I delta x's, but then go backwards just a half a delta x unit to get into the midpoint of that interval instead of the right side of the interval. So this is going to be our left side, pi over 4, plus I multiples of delta x. Delta x was this, so we've got pi I over 4n, and then minus a half of this. So a half of this is going to be pi over 8n. I think we can take pi over 4 and pi over 8. Nah, let's not bother combining anything. We'll just have 3 terms. That's fine. Okay, so that is our that's our xi bar. That's our midpoint formula. Midpoint abbreviated there. Okay. This is just nuts. This is just nuts. Midpoint. There we go. All right, so now to set up the Riemann sum, we just say, hey, we have to add up from I equals 1 to n the function evaluated at the midpoint of the ith interval times delta x. This is the height of the rectangle times the width of the rectangle, just like that. Pretty easy to do. We'll do f of pi over 4 plus pi I over 4n minus pi over 8n, and then times the pi over 4n. Now, we can have Desmos do most of the heavy lifting for us. Okay, what I have said that you're allowed to do on this assignment is have Desmos evaluate functions and sums. So, here's how we can get Desmos to do the heavy lifting. We can say, all right, this function here, this is going to be called f of x, or whatever you want to call it. F of x would be fine. That's our function. And now we're going to sum. I'm going to call this I equals 1 to n. And we need an n value. N equals like 10 or something. So n is a parameter we'll be using. Now what we're going to do is just type in f of, and then I can do pi over 4 plus pi I over 4n, and then minus pi over 8n, all of that, and then times by pi over 4n. And there we go. And now there is our approximation of this integral using 10 rectangles. So if I use 100 rectangles, I get that. If I use 1,000 rectangles, I get that. Any prediction about what this integral equals? It appears to equal 1. Let's actually do it and see if it's correct. We can double check our work by actually typing in the integral directly. 2 over 2 sine x minus cosine x squared dx. And yes, it does say that it equals 1. Wow. I'm kind of surprised that it equals 1. I feel like since it equals something so simple, maybe there actually is a way to do this Maybe there is some clever approach to this that doesn't require something like a Riemann sum. Now I'm curious. That's okay. We'll leave it at that. There might be some way to solve this that doesn't, that's not just an approximation, but that's there's got to be. If it equals 1, oh man, I'm gonna ask Wolfram Alpha. I'm gonna ask Wolfram Alpha. I can't think of anything. No, I shouldn't. I shouldn't ask Wolfram Alpha. No, I'm not gonna spoil it. I'm gonna look at that later and see if I can figure out some way to do that. I really feel like if it equals something so simple, there should probably be a way to do it. Anyway, though, that is a demonstration of how you can go back and use Riemann sums. Okay, so all we're having the computer do for us is evaluate functions and add up numbers. Okay, that's all it's doing, evaluating functions and adding up numbers. So we're not, this technique is not relying on Desmos's ability to evaluate integrals. That's what we did to check our answer, but we did it more rigorously than that. Okay, with our own work here. Okay. So shall we move on to the next thing? So I asked before class, what else should we do today? What do you want to see today besides an example of doing area? And there was a suggestion to see a tangent line of a parametric curve. But we're going to have a parameterization of that tangent line. Okay, so keeping everything in parametric terms. So first of all, let's come up with a good curve to use. So I kind of like, I'm kind of into this function here, this r equals sine theta function. It's a circle, but it's like a circle, that's situated sort of up, sticking out from the origin as opposed to centered at the origin. So if we wanted to parameterize that, we could. It would be sine theta cosine. Actually, I guess we could say sine t cosine t, and then sine squared t, like this. Okay, because that's r times cosine of theta, and then r times sine of theta, and then using t in place of theta, you get this. And if we have theta go from 0 to like pi, we get the whole circle. Pi over 2 would be half the circle, whatever. So if we want to use this and select a particular t value, like say pi over 4, I can do that. I can plug in pi over 4 everywhere. And that gives us that point right there. Oh, that's not a very interesting point, actually, because that's going to have a vertical tangent line. Oh, I don't want to do that. Let's try pi over 3 instead. Pi over 3. Pi over 3. There we go. We'll do that point. Okay, so here's a parameterization of something. Here's a point. We're going to try to find a parametric description of the tangent line at that point. Oops. That'll do. Okay, so we have our two functions, x equals sine of t cosine of t, and y equals, well, let's put it over here actually, y equals sine squared t. So what we learned before is that the slope of a tangent line is going to be y prime of t divided by x prime of t, right? It's the derivative of y with respect to t divided by the derivative of x with respect to t. This gives us dy over dt, or dy over dx. Okay. So we're going to want to know the derivatives of the x prime. We'll take a derivative of this. Here, I guess it's a product, so we're going to have to use the product rule. We have sine, derivative of sine is cosine, so we get cosine times cosine is cosine squared. And then plus sine times the derivative of cosine, which is sine times negative sine. So that's actually going to yield a minus sine squared. And then for y prime over here, we're going to get 2 times sine of t, and then times the derivative of sine of t using the chain rule. So here we're using the power rule and the chain rule. And that would be cosine of t. Now, if I am not mistaken, this is cosine of 2t, and this is sine of 2t. Am I right about that? Let's double check our super ultimate trigonometric identity compendium. All right, where are you? Oh, it's in the Calc1 folder. Trig identities. Let's see if I remembered my trig identities. Double angle, formulas, double angle. Yes, sine of 2x is 2 sine x cosine x. And cosine of 2x is, among other things, cosine squared minus sine squared. 2 sine x cosine squared minus sine squared. Yes, there we go. So there's x prime and y prime. So now the slope of the tangent line is like y prime over x prime. So that'd be sine of 2t over cosine of 2t, or in other words, tangent of 2t would be the slope. But if we want to describe the tangent line at a specific point parametrically, I don't actually want to do this. I don't actually want to get the slope. Let me show you what we want to do instead. First of all, we want to evaluate at our point. Let's evaluate at x equal, or t, sorry, t equals pi over 3. Okay. Okay, so x prime at pi over 3 is going to be cosine of 2 pi over 3. 2 pi over 3 on the unit circle is going to be here. So cosine of that should be -1/2. So this should be -1/2. And then y prime at pi over 3, sine of 2 pi over 3, this should be up here, square root of 3 over 2. This is just from me having the unit circle memorized. Okay. You don't remember your unit circle, not a big deal. Okay. You can always look it up. Or just use a calculator. Okay, so there's our x and our y, right? Now, instead of finding the slope, what I want to do is come to this point over here and say, what if from this point, what if we have a change in x, delta x equal to -1/2, which is the, which is our x prime at that point right there, and then delta y equal to √3 over 2. Okay, from this point, 1/2 is this far. So delta x would be going back to about, oh no, get out of here. There we go. Going back to about there. Okay. Yep, going back to there. That's 1/2 a unit. Okay, this far, measured to the left. And then we have square root of 3 over 2, which is going to be up by about, I'm going to eyeball it, about that far. Square root of 3 over 2 is 0.87, about that far. If we change x and change y by that amount, we get this. Plop that point a little closer where it should be. Okay, get that right there. Now, I want to approach a parametric description of the tangent line. Okay, the tangent line is going to be, the sort of line that extends out in this direction. For the purpose of finding that parametric description, I'm going to make a little vector here. This is called a tangent vector. And so from this point, we could add this tangent vector. And this tangent vector has these derivatives of x and y with respect to t evaluated at this pi/3 angle, right, that we're corresponding to here. So at that point there, we have those values, right? Those values make a little, we could use them as the x and y for a vector. And then now that we have this tangent vector, what we can do is say, hey, let's take the position of this point, which we'll call P, and we'll think of that point as a vector as well. And we'll say, take that P and add some multiple of the tangent vector. So this is a weird way to make a function. It's called the vector form of a line. It's a point interpreted as a vector. So the coordinates of that point as a vector, plus t, which is a parameter, the parameter t, times another vector. So what this means is essentially we have this point P. So this is the vector P. Okay, if this is just the point P, the vector P is a vector from the origin that points to that point, right? So that's the point P interpreted as a vector. And then what we're going to do is add to that. And if you've studied vectors, vector addition is added like tip to tail. So we put on the tip of that vector some multiple of this vector, which means we could go 0. We could do a 0 multiple, or like a small fraction multiple, or a larger multiple, or an even bigger multiple, or a really big multiple. Or we could do a negative multiple, some negative multiple, and go backwards this direction. And if you let that multiple be any value, then you get from that all of the possible points on that entire infinite tangent line. So this is your parametric. This basically is how you get your parametric description of a tangent line. Now, if we go in there with a little more detail, we can get the point P. So the point P is, if we just plug our pi/3 into the original description of the curve, we get, we would get, so let's see, at t equals pi/3, we'll get sine pi/3, cosine pi/3, comma sine squared pi/3. And this ends up being √3/4, I believe. √3/4, comma 3/4, I think. Did I do that right? So square root of 3/2 times 1/2, and then square root of 3/2 squared. Yes, that's correct. And so then that's the coordinates of the point. I'm going to add to that this t multiple of the vector, which comes from the derivatives. And the result is this parametric description, which I'll now put in the xy format. Square root of 3/4 plus t times -1/2. So I'll write minus 1/2 t. Okay, so t times this -1/2. And then the other one is the constant 3/4 plus t times the square root of 3/2. Like that. And now we can graph it, make sure it all works. Okay. I'll graph square root 3 over 4 minus a half t, comma 3/4 plus square root of 3 over 2 e as well. And there is what that line looks like if you just have t go from 0 to 1. T going from 0 to 1 is literally just add none of that vector to add all of that vector. So the line segment that we get if we have t go from 0 to 1 is the line segment that lies exactly on top of that vector, where that vector would be. That's why it looks like that. That looks exactly like the vector I drew, right? But if we let t range outside of that value, like if we let it go back to -1, now there's a negative version of that vector. Here's the point minus that vector. And if we go, if we let it go -infinity to infinity, we get the entire range of the entire line, what's called the span of that vector, which is starting from that point, adding all of the possible multiples of that vector gives you all of the points along the straight line. So so guys, Calc3 is all vectors all the time. Okay, so you start thinking about functions in terms of vectors more and more and more, and everything, and vector functions are parametric in nature. So like, get ready for lots of this coming up. Okay. The other thing that's cool here is the concepts at play here are also really, really important in linear algebra. The idea of like scalar multiples of a vector and what's called the span of a vector, very important in linear algebra. So if you plan on taking that next semester in the fall, yeah, we'll talk about this kind of thing there too. You guys have any questions? I'll just, for the notes, I will go ahead and put this in there so you can see it. Yeah, here we go. Going to make everything here a little bit smaller. Pick it up there. And get this guy at the bottom. All right. I think that's it for the day, folks. Have a lovely weekend, and I'll see you Monday.